Today's lesson for 2/6, the outcome is I can calculate enthalpy or heat change for chemical processes using a variety of methods. So we're going to be going over some pen and paper methods that we can use to calculate the heat change for a chemical process. Instead of using experimental methods, these are some ways that we can do this with pen and paper. So for your drill, the reaction below is the combustion of gasoline, which occurs in gas-powered vehicles. The molar mass of gasoline, which is C8H18, is 114.22 grams per mole. So a gallon of gasoline weighs about 2,800 grams. How much heat energy is released when a gallon of gasoline is combusted? And then question 2, how many liters of CO2 are produced? So go ahead and pause and take a few minutes to work this question. So to find our answer here, we're going to need to do a little bit of stoichiometry here. We know that whenever 2 moles of gasoline react, that we're going to get this amount of energy released. So we're going to need to convert our mass of gasoline from grams into moles and then use that molar relationship to determine the amount of heat. So I'm going to start with that 2,800 grams of my gasoline over 1. My first step is going to be to convert this into moles. So 1 mole of gasoline, the molar mass was given to you. So that's 114.22 grams. So this will tell us how many moles of gasoline we have. Now we're going to use the equation to get from moles of gas to heat. So from the balanced equation, we know that for every 2 moles of C8H18, we're going to release this amount of energy in kilojoules. So solving my answer, here's what I get. And I just went ahead and rounded to the ones place. For the next question, it says how many liters of CO2 gas are produced? So there's a couple different ways you can approach this. You could start with the amount of energy released and then work backwards to get the amount of CO2. Or we could also still start with our same given, which would be our mass of gasoline. So this is just going to let us convert from grams into moles like we did in the previous question. And from my balanced chemical equation, I know that for every 2 moles of my gasoline, that I'm also going to produce 16 moles of carbon dioxide. And then lastly, we don't want our answer in moles, we want it in liters. So 1 mole of any gas is 22.4 liters. So this gives us a volume, I'm going to round to the ones place, of 4,393 liters, and that's per gallon of gasoline. So we're going to be working on classwork 4, which is enthalpies of formation and reaction. So again, we're looking at ways that we can calculate the heat change for chemical processes without having to do experiments. So one way that we can do that is called Hess's law of heat summation. So this was a Russian chemist who determined that the change in enthalpy for a chemical change is independent of the path that the reaction takes. The path independence of the energy in reactions is referred to as Hess's law. So when we talk about something being path independent, we mean that the only thing that matters is the starting and ending states. The way we get from point A to point B is not necessarily important. So a good example of this would be like altitude. So if you go to climb a mountain, whether you climb straight up a sheer cliff face or you go up a path that's a switchback path, you're still going to have the same change in altitude regardless as to how you climbed the mountain. So here I have an apple being dropped from a shelf. and I have the direct path. So suppose an apple, which is the system, falls from a shelf to the floor. It hits the floor and it's going to release a certain amount of energy. Now, if you lift the apple above the shelf and then drop it, it's going to hit the floor with greater energy. But the net energy released is the same in both cases when you account for the extra energy that the apple had to absorb as you lifted it. So my net energy release is the same regardless as to which path I take to drop the apple. So why does the direct path and indirect path have different activation energies? The direct path involves the energy needed to just push the apple off the shelf, whereas the indirect path involves lifting the apple up against gravity. This is going to require more input of energy before dropping it. So that's why we have a larger activation energy for the indirect path. How does the net energy compare for both paths? So the net energy released is the same for both paths. The indirect path requires a little bit more initial energy input to lift the apple, but this is balanced by the greater energy that is released when it falls from the higher position. So we're going to take advantage of this to calculate the heat change for a reaction using Hess's law. So Hess's law of heat summation allows you to determine the heat of reaction indirectly by using the known heats of reaction of two or more thermochemical equations. You can add the heats of several reactions to find the heat of the desired reaction. So let's consider the conversion of diamond to graphite. So this process, we can't measure this directly because it takes thousands and thousands of years. So I can't do an experiment to figure out delta H because this reaction just takes too long. But I can look at some other reactions. So these two reactions here, this is the burning of carbon as a diamond and the burning of carbon as graphite. And we have delta H for these processes. This I can do experimentally. So I can just do these two reactions and measure this delta H. But I can't do reaction A and measure delta H because it's too slow. So I'm going to leverage these two reactions that we know the delta H of in order to calculate delta H of this reaction. Now, when you look at the equations, you can see that there are some components. So, for example, here we have carbon diamond, which is our reactant, and here we have carbon graphite, which is our product. So there are some similarities between these two reactions. So the first thing I'm going to do, I'm going to take reaction C and I'm going to flip it. So I'm going to make the products into my reactants and the reactants into the products. So I'm just going to reverse the reaction. So I have CO2 gas, and that's going to decompose to give me carbon graphite and O2 gas. Now, since I am reversing the direction of the reaction, I'm also going to reverse the direction of delta H. So in its original form, it's exothermic. But when I flip things around, now it's going to be endothermic. So I'm switching the sign on that delta H value. So now I'm going to use reaction B and reaction D, which is the one we just reversed. So if I go ahead and put this here, my delta H, put this guy here, and my delta H, remember we flipped this, so now it's positive. So now what I'm going to do is I'm going to add these equations together. Now if you look, there are some things that are the same on opposite sides of the arrow. So like this CO2 is going to cancel out this CO2 because they're on opposite sides of the arrow. Same thing with oxygen. So here oxygen is a reactant and here it is a product. So I can cancel that out. So what does that leave me with? My only reactant is carbon diamond and my only product is carbon graphite. So I got to this equation A by combining equations B and D. So I'm going to get the delta H by combining the delta H of these two reactions. So I get positive 1.9 kilojoules. So this reaction that I can't measure directly because it takes too long, I can measure it indirectly using reactions that I can do and that I can measure the heat change for. Now, some other rules. Normal algebraic relationships apply whenever you are canceling things out. So for example, see how we have this 3a, this c and this c, that's going to cancel. D cancels. See how I have 3a and 1a? So that 1a will cancel and I'll be left with 2a instead of 3a. So this would be my summed reaction. Now you can also multiply a reaction by a whole number, so long as you multiply delta H by the same whole number. So for example, A plus B gives C has a delta H of 10 kilojoules. If I double that reaction, I'm going to double delta H to 20 kilojoules. So let's take a look at number 3 together. So I gave you answers for numbers 3, 4, and 5. We're going to do number 3 together, and then I'm going to give you some hints for 4 and 5 for you to practice on your own. So first, this is our desired equation. This is our goal. So we're trying to combine these two equations in such a way that I get the desired equation. So let's take a look at my first reaction. You'll notice that Al solid, 2 of them, is a reactant. So I don't want to flip this reaction. We also notice that the numbers match, right? I have 2 Al and 2 Al. On this side, I have one of these aluminum oxides. So I'm just going to keep this first reaction the same. I'm not going to do anything to it. So since I kept that reaction the same, we're going to keep the delta H the same. So again, this blue reaction, this is my goal. This would be that first reaction that I kept the same. I didn't need to flip anything or multiply by anything, so I'm keeping my delta H the same. Now for the second reaction, notice that this 2Fe solid, here it is a reactant, and here it is a product. We also see that this Fe2O3 is a product here, but in my desired reaction, it's a reactant. So that's a hint that I'm going to need to flip this reaction. So I'm going to flip this reaction. I'm going to make Fe2O3 solid my reactant, and the solid 2 moles of iron and 3/2 mole of O2, those are going to be my products. Now, since I flipped the reaction, I'm also going to flip the sign on delta H. So this one was flipped, which means the sign of delta H is also flipped. Now we're going to check to see if this actually results in my desired equation. So this 3/2 O2, those are going to cancel. There's nothing else that cancels. So the only thing I'm left with is my 2Al solid as a reactant, my Fe2O3 as a reactant, my 2FeS as a product, and my Al2O3 as a product. So if I combine these two red equations, 1 and 2, it's going to result in my desired equation. So if I want to get delta H for this reaction, I just need to combine these two values to get delta H for the reaction. So for question 4, some hints here. So one of these reactions is going to be flipped. And to make the equation match the goal equation, you're going to have to divide everything by 2. That means both the equation and the delta H. For question 5, one of these reactions must be flipped and another one must be doubled. So go ahead and pause the video and take some time to work questions 4 and 5. The answers are on your page in your unit packet. So Hess's law is one way that we can indirectly find delta H without having to do a reaction. We use reactions that we know the delta H of and manipulate them to match the desired reaction. Another way that we can find the heat for a reaction is through standard enthalpy of formation. So the standard enthalpy of formation, which is represented by this symbol, of a compound, is the change in enthalpy when 1 mole of the compound is formed from its elements, with all substances in their standard states. So standard state is the stable form of a substance at a temperature of 25 degrees Celsius and a pressure of 100 kPa. The standard enthalpy of formation for a free element in its standard state is set at 0. So let me show you what I mean here. Here we have a reaction that is for the formation of water. Now this reaction is exothermic. We can tell that because the enthalpy of my reactants is higher than the enthalpy of my products. So the way we're going to do this, we're going to look at the standard enthalpies of formation for our reactants, which are H2O2, and my product is H2O liquid. So essentially, my reactants here are starting off with a value of 0, and my product has a value of negative 285.8. So this means that for my reactants to become products, they're going to need to release 285.8 kilojoules of energy. So by using the values in this table, I'm able to figure out what delta H of this reaction is without having to actually do the reaction. So let's take a look at number 6. It says to identify the standard states of the elements that make up CO2, then sketch the enthalpy diagram for its formation. We're going to use the table that we just looked at in the previous slide to get these values. So let's start by writing up our reaction here. So we're going to start with carbon, and this is going to be in the graphite form. And we need to react that with O2 as a gas to produce my CO2 gas. So this is my equation here. Now I'm going to look up the values on my table. So looking at carbon graphite, I see that delta H is 0. And looking at O2, I see that my delta H is also 0. So for CO2 gas, here is the value. So essentially we have 0, 0, and then negative 393.5. So for my reactants to become products here, we need to release 393.5 kilojoules of energy. So when I draw my enthalpy diagram, since this is exothermic, I'm going to start with my reactants up here. That would be my carbon, graphite, and my O2 gas. Those are my reactants. And then my products are going to be CO2 gas. So in order for my reactants to become products, we need to release negative 393.5 kilojoules. So for a reaction that occurs at these standard conditions of 25 degrees Celsius and 100 kBa, you can calculate the enthalpy of reaction by using those standard enthalpies of formation. So the change of enthalpy when 1 mole of matter undergoes a chemical reaction at standard conditions is called the standard enthalpy of reaction. This little symbol here, this degree symbol, that's telling us that it's in the standard state. So the standard enthalpy of reaction is the difference between the standard enthalpies of formation of all the products and all the reactants. So I would add up all the values for my products and add up all the values for my reactants, and then I'm going to subtract the two. So let's take a look at number 7, and then I'll give you some time to practice with 8 and 9. So looking at my reactants here, notice that I have 2 moles of SO3. So I'm going to need to find the value for SO3, and I'm going to double that. So for my products, I'm going to get 2 times negative 395.7. So that's going to be my products. Now I need to subtract from that my reactants. So I have 2 reactants here. Notice there's 2 moles of SO2, so I need to double this value. So 2 times negative 296.8. And my other reactant is O2. So I'm going to add that. And there's 1 mole of O2. And the value for O2 is 0. So to do this math, I'm going to need to do this negative 791.4 minus my total here is negative 593.6. Notice that we have a double negative, so we're going to end up adding this number. So when I do my math here, I end up with negative 197.8 kilojoules. So I've just figured out that this reaction is exothermic and that heat is a product. So I'm going to release this 197.8 kilojoules. For question 8, you're going to do a similar process. Your answer is going to be negative 566 kilojoules. For question 9, your answer is going to be negative 113.04 kilojoules. Now, another enthalpy that we can find is the enthalpy of solution. So when a substance dissolves in water, heat is either released or absorbed. The energy change that happens when 1 mole of a substance dissolves is called the molar enthalpy of solution. So you guys did an experiment at the beginning of this unit where you took some salts and dissolved it in water to measure the temperature change. So we can actually quantify the amount of heat released there using enthalpy of solution. So whenever you dissolve something in water, there's kind of 2 processes that are going on here. So water molecules are polar, meaning they have a positive end and a negative end. These ends attract each other and help water molecules to break apart solids, especially ionic solids. So to dissolve a substance, the forces that hold the solid together must first be broken. So this is like step 1. We have to break those attractive forces. And this is going to be an endothermic process. You've got to put energy in to break that attraction. Then water molecules surround the dissolved particles, forming solvation shells, which releases energy. So that's sort of like step 2, which is exothermic. So depending on which step is bigger, the dissolving process might be endo or exo. So for example, here at step 1, we absorb this amount of energy in order to break those bonds, and then we release this amount of energy. So the net difference between those two gives us a positive delta H of solution, meaning that this is an endothermic process. So this would mean that the temperature of the water would go down because it's absorbing energy away from the water. In my exothermic example, we see that the energy released in step 2 is much greater than the energy absorbed in step 1. So this gets us a negative delta H of solution, or an exothermic reaction. So inside of a cold pack, there's 2 sealed plastic bags, one inside the other. The outer bag usually contains ammonium nitrate crystals, and the inner bag contains water. So when you break that inner bag, you release the water, and that ammonium nitrate dissolves in the water. So the overall enthalpy of solution is the difference in energy needed to break the solid's bonds and the energy released when solvation shells form. So suppose you are designing an instant heat pack. Would you want to select a compound with a positive or negative value of heat of solution in water? So if it's a heat pack, we want the process of dissolving to release energy. So we want a negative value. We want an exothermic dissolving process because we want to release heat as the solid dissolves. Now for number 11, you're going to need to look at the data that you collected in classwork 1 for the hand warmers experiment. So first you're going to calculate the heat transfer when ammonium chloride dissolved. So you're going to need to use the total mass of the solution, which means water plus solid, the specific heat of water, and the temperature change of the water. So Q is what you are solving for. M is the mass of the solution, which means water plus the mass of your solid. C is 4.184 joules per gram degree Celsius. That's our constant specific heat. And then we need to find delta H. So that's going to be the final temperature minus the initial temperature. And then you're going to plug that in and solve for Q. Now for B, how many grams of ammonium chloride were dissolved? Convert the grams into moles. You will need to find the molar mass of ammonium chloride to do this. So the molar mass of ammonium chloride is 53.49 grams per mole. So you're going to need to take your grams and use molar mass here to convert them into moles. Then you're going to find delta H solution for ammonium chloride in joules per mole. So delta H solution is going to be the number of joules, which you're calculating by Q, divided by the amount of moles of solid. So Q is what you got in question A, and moles is what you got in question B. So you'll have to divide those two to get your answer. So go ahead and pause the video, work on question 11, and then return here when you're ready for question 12. So number 12 says, when 1 mole of NaOH is dissolved in water, 44.5 kilojoules of heat are released. So this is telling me that this is an exothermic process. So when I take NaOH and I dissolve that in water, I get Na plus, and I get OH minus, and I also get 44.5 kilojoules of heat being released. So if I had 1 mole of NaOH being dissolved, I would release this amount of heat. I don't have 1 mole, I have 2.50 moles. So starting with my 2.50 moles of NaOH over 1, I know that for every 1 mole of NaOH, I'm going to release 44.5 kilojoules of energy. So when I solve here, I'm going to get this answer. Now it's important to note that this is exo and that energy is released. So I'm going to put a negative sign in front of my energy per mole, which means my answer is also going to have a negative sign.